So question 16, even though I've got it covered up here, I guess I can move that a little bit higher. Which of these electron configurations are appropriate for the common ion formed by alkali metals? All right, so alkali metals are our group 1 metals. Our group 1 metals, they react and they form a +1 cation. And they do that by losing their only valence electron. So if we look at lithium, for example, lithium is 1s2, 2s1. Lithium's going to react and it's going to lose its one valence electron to become lithium +1. And the electron configuration of that will be 1s2 because it lost that one electron. So we are looking for the electron configuration of group 1 metals after they react. They're all right here in the periodic table. So after they react and lose one valence electron, they should be isoelectronic with a noble gas. They essentially should have a noble gas electron configuration. So we start off with 1s2, 2s2, 2p6, right? That's the electron configuration of neon. And that would also be the electron configuration of sodium +1. Sodium loses its one valence electron, it becomes neon, right? So that's fine, that equals sodium +1. 1s2, 2s2, 2p4. Nope, there's no way we're going to lose that many electrons. So we can cancel out B. 1s2, yep, we know that equals lithium +1. Choice D is 1s2, 2s1. Nope, that is lithium itself. That's not an ion of lithium. And then, so I don't have to skip to the next page. What is choice E? I think choice E is also an answer. It's like neon, 3s2, 3p6. Is that choice E? Yeah. And that's also, right, that's the electron configuration of argon. And that would also equal, right, potassium. If potassium were to react, that would be potassium +1. That would also equal that electron configuration. So A, C, and E, all of those electron configurations could correspond to a group 1 metal as an ion, right? After it reacts, it's going to lose that one valence electron, making it isoelectronic with a noble gas. All right, 21, 22, 24, and 25. All right, so getting into our calculation questions, 22 will be a nice break from our calculations, right? So gravity waves have the same velocity as light and a wavelength of 1 × 10⁶ meters. What is the frequency of that? So we're given wavelength and we're asked for frequency, right? And we know it moves the speed of light. So we're looking for speed of light equals my frequency times my wavelength. Here we're looking for frequency. So I want to divide both sides by wavelength. That cancels out. So I get the frequency of this equals speed of light divided by my wavelength. Speed of light's already in meters, so I don't have to do any unit conversions there, right? Frequency equals 3 × 10⁸ meters per second. That's my speed of light divided by my wavelength of 1 × 10⁶ meters. All right, so meters cancel out, and what is that? Is that 300? Someone want to confirm if that's 300 for me, or I'll just, yeah, all right, thank you. No one says anything, just leave me here. right? So 300 cycles per second. Yeah, Josephine, I would check your formatting. Did you put this in parentheses when you put it into your calculator? Because yeah, it should be 300. And then to answer the question, the other question that came in, do we need to know the difference between radial and angular nodes? No, Karine. We just introduced the idea of a node as basically a region where there's zero probability of finding an electron, but you don't need to know the difference between those two. Excellent, Josephine. Yeah, there's a lot more that was in the reading. Like, I would focus more on what we covered in class. For question 22, what is the maximum number of electrons that can have n equals 4, L equals 2? So an n equals 4, we're at the fourth quantum level, but that's not what's important here. What's important here is that L equals 2. When L equals 2, we're talking about d orbitals. And anytime I have d orbitals, we're going to have 5 d orbitals, right? So 5 orbitals, 2 electrons each, right? For a total of 10 electrons that we can hold in those d orbitals at the fourth quantum number. And yeah, answer with numbers only. Don't try to put electrons in there. Question 23, I just kind of added this in because I thought it was kind of interesting to think about, right? All this chapter focused on speed of light, electromagnetic radiation, which is moving the speed of light, but the same wavelength and frequency relationship also pertains to sound. It's just not moving the speed of light, it's moving the speed of sound. But we can still use that same equation to basically say speed equals my frequency times my wavelength. And yeah, let me just jump back to question 22 real quick, because I was thinking the same thing, Sam, because I kind of glossed over that, but you're right. The fact that n equals 4 is important, right? Because it's important because if I said, you know, n equals 1 and L equals 2, what would the answer be to that question? How many electrons are there? Do I have d orbitals at the first quantum row? Yeah, Lucy's correct, right? There's 0 electrons because n equals 1 is my first energy level. I only have an s orbital. L equals 2 is trying to tell me there are d orbitals there. I don't have d orbitals at the first energy level. So Lucy's correct when she says there's 0 electrons. So yeah, thank you for saying that, asking that question, Sam, because when n equals 4, I can have d electrons. But if n equals 1 or n equals 2, no, d electrons don't exist. So the answer would have been 0. Yeah, so I kind of glossed over the 4, but you're right. I should have checked and say, okay, n equals 4, so L could be 3, 2, or 1. All possible choices. Yeah, the L tells us, right, what orbital we're dealing with. Right, when L, yeah, right, when L equals 1, when L equals L equals 0, 1, 2, or 3. When L is 0, that's telling us we have s orbitals available. When L is 1, that's telling us we have p orbitals available. When L is 2, those are talking about our d orbitals. And when L is 3, that's talking about our f orbitals. All of this is in the periodic table as well. It's basically telling you at the first energy level, you know, n equals 1, L is 0, we only have an s orbital and only an s orbital, no more. When n equals 2, we've got s and p orbitals. You see the same thing in the periodic table. Yeah, and so the other thing that came up, right? I don't know how to pronounce your name, Rahel, who said 32, right? 32 would be the total number of electrons at n equals 4. That would be at all orbitals, s, p, d, and f. There are 32 electrons at n equals 4. We're just asking about L equals 2. So we're just asking about the d orbitals only at n equals 4 for that question. But yeah, it's important to make sure that the L we're asked about corresponds to the quantum, or is available within the quantum number we're looking at. Yeah, so back to question. Oh, my mistake. I don't think anyone asked for question 23, but someone asked for question 24 and 25. So we didn't have to do 23 anyways. All right, 24 and 25. All right, everyone's going to go out and buy a radar detector now, or a radar jammer. Right, a police radar detector operates on a frequency of 15 gigahertz. What's the wavelength of this in meters of this frequency? So this is a variable. So this is not going to be the same question to question. So does someone want to tell me how many gigahertz they're given in this question? All right, so we've got 18.9 gigahertz. And so 18.9 gigahertz, we got to get that to hertz first. And we know in 1 gigahertz, there is a billion hertz. So 1 times 10 to the 9 hertz. So that is 1.89 times 10 to the 10 hertz. And we know that 1 hertz equals 1 inverse seconds. So we can go directly from hertz to inverse seconds. So I've got 1.89 times 10 to the 10 inverse seconds. Now I've got my frequency in the units that I needed in, and now I can find my wavelength of this, because right, speed of light equals frequency times my wavelength. Divide both sides by frequency, that cancels out. My wavelength equals speed of light divided by my frequency. My wavelength equals my speed of light is 3 times 10 to the 8th meters per second. All over my frequency, 1.89 times 10 to the 10. I divide, seconds cancel out, and that's good because I'm looking for units in meters. So let's see, what does that give me? 3 times 10 to the 8th divided by 1.89 times 10 to the 10. So your initial number might be a little bit different, but the steps would be the same. So for Michaela's question, right, I get 0.1587 meters. So to 3 significant figures, right, I would say 1.59, e to the minus 2 meters, because we want to move that decimal place over twice, and we're going to have to round up because we're dropping, everything after the 8. So your initial number might be different, but the steps to solve that problem 24 are going to be the same. And then 25, hopefully 25 wasn't too bad. Yeah, through the unit conversion, Sandra, because we're going to convert from gigahertz to regular hertz. And we know in 1 gigahertz, I have a billion hertz. So 1 times 10 to the 9. So I multiplied 1 times 10 to the 9 by 18.9. So move that decimal place over 1, and it goes from 10 to the 9 to 10 to the 10 through that calculation. Josephine, it could be a rounding issue. And it could be maybe you've interpreted the number wrong, because you did say 2.31. It might be 23.1, right? Is it 2.31 e to the 1? So that's what I would check. All right. What section are you in? I can go look on the back end. Yeah, wait. All right. Yeah, that's what I thought. So question 25, we've done a few questions like this in the homework, right? About energy of a lamp, this wavelength, how long it was on for, right? This is very similar to that. We've got a 0.5 watt laser, it's 585 nanometers, it's on for 10 seconds. You know, how many photons of light are released? So first things first, right? We've got a 0.5 watt laser, which we know is 0.5 joules per second, right? They tell us that 1 watt is 1 joule per second. And we run this laser for 10 seconds, right? So we're going to release a total of 5 joules. So now I want to convert this wavelength of light, 585 nanometers, and find out how much energy is in 1 photon of that light. And then I can say, okay, how many photons would I need to make up 5 joules of energy? So that's our next step. And on the exam, right, you might see wavelength in meters, you might see it in nanometers. It just depends on the question. So I would expect both. So let's see, 585 nanometers, right? I know in 1 meter, I've got 1 times 10 to the 9 nanometers. So my wavelength is 5.85 times 10 to the minus 7 meters. Now I can find the energy of 1 photon, right? So energy equals, this is the first time this equation's shown up tonight, but you definitely need to know how to use this equation. Energy equals Planck's constant times the speed of light divided by my wavelength. That lets us relate wavelength to energy directly. So the energy for 1 photon equals Planck's constant 6.626 times 10 to the minus 34 joules times seconds. My speed of light, 3 times 10 to the 8 meters per second. All over my wavelength, 5.85 times 10 to the minus 7 meters. So I'm going to get the energy for that. And correct, Alessandra, yeah. Valence electrons are anything beyond the noble gas core electrons. So divide that by 5.85 times 10 to the minus 7. And I get the energy to be, the energy for 1 photon to be 3.3979 times 10 to the minus 19 joules. And that is joules per photon. All right, so our last step, I need to have 5 joules of energy. And I know for every 1 photon, I'm going to have 3.3979 times 10 to the minus 19 joules. So joules are going to cancel out, and we're going to be left with numbers of photons, right? So let's see, 5 divided by that. And I get like 1.47 times 10 to the 19 photons. I need a large number of photons to come up with all of that energy. Any questions on 25?